It's a pleasure to be here, and welcome to this last talk before lunch. I'll dive right into the quantum future. So what we're seeing right now is furious developments and a race towards the first useful quantum computer that can do actual calculations or can provide solutions to problems that need solving and that cannot be solved with computers right now. So these quantum computers, eventually to become really useful and available to many more people, will need a communication between them. So we'll need a quantum network. And this is also what Kian already told us. We'll need a connection to connect people to quantum computers and between quantum computers themselves. And this cannot be done with a standard classical connection because qubits don't work that way. So what we need is to provide entanglement between quantum computers, entanglement between users and a quantum computer. So basically what we need is a quantum network where we use qubits to send information. What we already heard this morning is quantum states can be shared between two places anywhere on Earth. And also, this is, I think, not come up this far, but any interference, any measurement on these shared states can be detected. These two aspects give really a different quantum communication, communication paradigm. This is what we use, and this is what we're aiming to build at QBird. So what we're aiming is to build quantum networks. We're originally a group inside QTech TU Delft, where we've been building on quantum networking and quantum cryptography for the past 4 years. We've recently spun out last year out of QTech, and we are now growing the team from 3 to already 8 people as we speak. What our goal is to provide the hardware and the software to enable quantum networks between users and between quantum computers and from users to quantum computers. The first generation of quantum networks are essentially networks that that provide a very simple quantum link. And this quantum link can already be used to exchange quantum keys. This is what we already also heard in the first 2 talks in this session. Basically, you provide a quantum key between 2 users. This key can be taken by a network encryptor and can be used in the standard classical network to secure communications. And because of the properties of these quantum bits and the entanglement between the 2 users, any eavesdropping or any attempt to interfere in the key exchange can be detected. And therefore, these keys are fundamentally secure against any eavesdropping. So what QKD is doing until now is there's one sender that sends a qubit over to a receiver, and thereby they build up a key between them. What we're doing at QBird, we use a slightly different approach, also because we're from QTech and we're already looking towards the vision, towards the future, where we want to connect multiple quantum systems and eventually want to connect quantum computers. So what we're doing is we're using a central hub where we perform a quantum measurement. And each user that wants to exchange key can connect to this central hub. And they only need to have a sender that sends out qubits. And between 2 senders of qubits, 2 users, the central hub can provide a quantum measurement, and then these 2 users have created a secure quantum key. So this is a slightly different overview of our architecture, where you can see the central hub connecting end nodes from user 1 and user 2. But because of the Bell measurement, because of the quantum measurement that we perform in the central hub, in the future we can use the same technology to connect processing nodes, other quantum sensors, quantum computers, anything that needs a entanglement generation to connect to the other side can eventually be connected with our central hub technology. So right now, what we can do is multi-point to multi-point connectivity, where any user in the system can generate key between any or together with any other user. This also provides for a very cost-effective scaling because the expensive equipment, the detector system, only needs to be provided once inside the central hub. So all the detection takes place here. This also inherently increases the security because inside the detector, the actual key is never known. So the detector itself is called untrusted, but actually it is very trustworthy because the key material simply is never there. So it cannot be taken from here. And as I already explained, this is really future-proof because we can use the same technology to upgrade it to more advanced quantum network technology. In the past few years, we have field tested our technology. We've taken it out of the lab and tested it with various industrial parties, network vendors, and really have proven the concept that we use right here. So how do we go from this QKD setup towards a full-blown quantum network? So our prototype system that we've been building up over the past 2 years has been put inside a testbed. We've tested it with various industrial players, but right now it's actually sitting inside a data center. I'll have a picture to show it in the next slide. And it is, actually performing quite well. So we've installed it June last year, and it's still there generating key and providing secure communications. The next step is to go towards a truly multi-user QKD setup that can connect multiple users, is also higher performant, and ready to install in more extensive networks. And for this, we're working together with the Port of Rotterdam. I'll tell a bit more about this later. This is a project that's ongoing as we speak. And next step is to really go towards a production line certified and also more scalable concept. And with more scalable, I mean it is easier to produce and smaller and easier to install in many different places. So for this, we're looking at integrated photonics. Of course, the system needs to be certified. And this is an ongoing project inside the EuroQCI program that I'll explain later. And as a final step, in parallel, we also eventually want to use the same technology to connect quantum computers. These quantum computers are not yet ready. We're not yet ready, but we're working towards this in a multi-year program called the Quantum Internet Alliance. We're really working towards entanglement-based quantum networks, photonic clients to connect to quantum computers, and ultimately enable quantum internet. So where are we right now? Right now, these are our prototype systems as they are installed inside the data centers of Eurofiber in Utrecht. This is a schematic of the system that is right there. So we have our central hub. It connects at the moment to end users. Distances are not that far, but they're, metropolitan distance. In total, 55 kilometers between the users. And we've tested this system multiple times, securing video calls, securing communications, and exchanging keys. Going from our prototype system, we're now working on a multiple user system that we want to install in a true piloting case. We're working together with the Port of Rotterdam, a Single Quantum, Innovation Quarter, and Quantum Delta to install a central hub and up to 4 end users to protect information inside the harbor of Rotterdam. So as you can imagine, this is a picture of the harbor in Rotterdam in the Netherlands. There's many information streams ongoing in a harbor. It's one of the largest infrastructure centers, and it's actually a very important economic hub in the Netherlands and in Europe. And if something goes wrong with information on boat transport, on loads, on maybe even the water levels, on the different quays, this can have truly disastrous effects. So between all these users in the harbor, there's many information streams ongoing, and we want to test and protect this using our system. So what we're going to do this year and next year is install the QKD systems in various locations inside the harbor, connected with optical fibers. There's already a couple of established use cases that we're going to test, and it is open for other users inside the Rotterdam harbor to connect. As a next step, and actually this is ongoing in parallel, we're working inside the EuroQCI program that the previous speaker from Airbus also told about, to build up quantum communication infrastructures in various member states inside Europe. So what we're doing there is mainly focusing on the industrializability of the QKD devices, strengthening the European ecosystem, and working towards certification that is really necessary for deployment inside operational environments. So we're doing this together with Single Quantum, who is working on the detector systems, Bright Photonics, who's working on the integrated photonics. We're providing all the quantum network software and hardware, and we're working together with Secura, who is a security company. Actually, it's a French-Dutch company that will guide us through the common criteria and certification, with ultimately the aim to have a fully certified system ready for deployment in the various member states and EuroQCI networks. And then taking a leap again and linking it also a bit to Kian's story, we're a partner inside the Quantum Internet Alliance, and this is the vision of a full-blown quantum internet inside Europe. This is not going to happen tomorrow, but it's a vision over the next 3 to 5, 7 years, where quantum processing nodes are connected via a hub to photonic clients or with repeaters to another quantum computing, quantum processor hub. And as you can see, the structure is already very well feasible with what we are building, with a central hub, quantum processing nodes, and nodes that we're going to work towards and move into a photonic client. So as QBird will be positioned here inside the Quantum Internet Alliance, and I would like to elaborate, if there's a bit more time, on one of the use cases that will be possible with these kind of networks, which is blind quantum computing. So what we will have is a photonic client, which is essentially a very simple 1 qubit quantum processor. And using a quantum network, this photonic client can send quantum data towards a larger quantum computer and perform a computation that, well, that the photonic client or that the user wants to do. Again, via quantum link, the results will be transferred back to the client, and not even the quantum computer or the company that owns the quantum computer will know what the calculation is or what the results are that they get out of this computation. So this is the future vision. And with this, I would like to leave you with a message. We're building the next generation digital infrastructure. Today, we're building secured communications, and tomorrow we'll enable general purpose quantum computing. Thank you.
We do have time for questions, if there are any questions out there. I'll go ahead and start, Ingrid, if I may. So I'm not expert enough to ask you a technical question, but I was impressed to see that you're working with these the Rotterdam harbor. And I recall maybe 10 years ago, there was some harbor, I don't know if it was Rotterdam or Hamburg, was hacked. and the controls, they couldn't do their shipping. And I'm just curious, do you get involved with some of the security experts in looking into those kind of case studies of security incidents in the past?
To be honest, well, we're working, of course, with the security experts in the Rotterdam Harbor.
Yeah.
I'm not familiar with this hack. Maybe, actually, Erwin Rijmaker, he's from the Port of Rotterdam. He might know this. But I don't know about the hacking. But we are working, of course, with the security experts
I think
of Port Base and Port of Rotterdam. So,
yeah, it's great to see that, because in our own work at QC, where we're quantum computing, it's early, but working with customers with real world problems, you learn a lot about what you really need to be able to deliver.
And this is what I mentioned with use cases that we're focusing on. The experts in the Rotterdam Harbor, they really know what is the information that needs most protecting.
Excellent.
What is most important.